But this is the page we're going to start with. You're going to notice I skipped a problem. We'll go back to it for sure. The reason I'm just skipping it is because it is more challenging. We haven't done this in a while, so I figured let's start with an easier one first. Then I'll go back to a more challenging one. Secondly, but before we do begin, I'll just kind of announce kind of like what my plan is from here on forward. I know we kind of took a short hiatus, starting this because I was more focused on my Regents classes. And our progress in calculus was actually pretty good, but now that delays kind of just keep on going, and I think like 20 states in our country have canceled school altogether. We're probably not too far behind in terms of that decision being made. So I'm going to start doing this at least twice a week, probably Tuesdays and Thursdays. So I'm going to kind of run it like a kind of like you would see in like a college setting. That's typically that's pretty normal, Tuesday, Thursday kind of class. And I'm going to kind of try to follow that format. You already have the rest of this unit, so I'm kind of glad I've always printed out the units for you, so that's good right there. I printed out the last unit already. It's at the school. It's going to get delivered to everyone, so you don't need to, you don't need to pick it up at the school. It'll get delivered to you on time too, because we still have to finish this unit. I made a Google Classroom. That way we can actually complete assignments, and you just do the assignments, take a picture of it with your phone, throw it in, submit it that way. You can put it in you can put the pictures in a Google Doc. You can submit the pictures directly, however you want to do it. We're not going to have as many assignments as we did when we were in school. I'm going to try to only do maybe one or two, every couple of weeks or so. Right now you're going to notice we're going to do the homework page now. You're not going to hand it in. I'm also going to weight homeworks a little bit differently. I'm going to try to grade differently because the third and fourth marking period, I'm sure if you've known in your other classes, they've now been combined into one marking period, which is, depending on who you are, it could be a really good thing, could be a really bad thing, especially if you had a weak beginning of the third marking period, because there was definitely a group of people who did not hand in a lot of work. Make sure you're not one of those people. Make sure you get that stuff in. It's going to be very important. If you're concerned about, maybe where your grade is and maybe what you're missing, please let me know. Ask me, and I can talk to you one-on-one. And then, probably through Remind would be the best, and I can tell you exactly what assignments you're missing. But you do have a long time to get them done, and so forth. So that's kind of all the kind of general announcements. I'm sure you've heard that from your other classes, and so forth. I typically try to go for about stream for 40 minutes. That's what I've been doing with my other classes. So I'll probably do the same with you. So we'll stream today. I'll probably do another stream on Thursday as well until we finish this unit. Okay? And then I'll probably assign maybe one thing through here. Yes, you'll be able to. I was just asked through Remind, can you watch these videos after? Yes, as soon as the stream is over, it will go. It goes right on to Twitch automatically. You just have to be aware that the beginning, the very first hour is going to be geometry. The second hour is going to be physics, and then you guys are the last hour. So you just have to manage it that way. I can also upload these on YouTube. I've been doing that with my geometry classes. Just because there's a lot of them and a lot of them don't make it every day. There's 7 of you, and if I know all 7 of you are here, I probably won't upload it, but I can make a regular routine of uploading them onto YouTube as well. The only problem with Twitch is they delete after about 7 to 10 days automatically. YouTube, obviously, they would just stay there forever, so I can kind of consider that. But yeah, I think that's all the general announcements I had. Today is really more of a day to review something we've done already, which was optimization. And we'll jump right into it. And one thing, just to let you guys know, I've had no contact with Mike Roberts, so if you guys could just throw him the information to the Remind, I'd appreciate that. Because he's the only one I have not been able to get in contact with. Alright, let's get started. And if you guys at any point have questions, you can just throw them in chat. You send him the information. All right. He hasn't joined the Remind. And I think he's the only one not here right now. I'm not sure. I think we're missing both mics, actually. All right. So, going back to this, I know it's been a while. It's been a couple of weeks since we've seen these things. Of course. And the goal is we're going to take the scenario. We want to find two equations. One we're going to take the derivative of. The other one we're going to use for substitution purposes. So in our first question here, it says a farmer wants to fence in an area of 1.5 million square feet in a rectangular field and divide it with half the fence parallel to one of the sides of the rectangle. How can he do this to minimize the cost of the fence? So this is kind of like a problem we've seen before. They give you this number right here. So since they're giving you a number in square feet, obviously this has something to do with the area of a rectangle. So the area of the rectangle, which is 1.5 million, and the way you calculate area is length times width. I'm going to draw a picture of our field, the area we're trying to make, and they want to put, so it's a rectangular field, but it says they want to divide it in half with a fence parallel to the other two sides. So cutting it in half, basically putting a piece right there. And ultimately, we need, one thing that we do know is the area that both of them take up is 1.5 million, and he wants to minimize the cost. So minimize the cost means he wants to use as little fence as possible. So you're maximizing the area by using as little material as possible. So we want to figure out how do we minimize the perimeter of this. But not just perimeter. Perimeter plus this piece right here. And what we're calling this, we can call this side right here, this is the length to our rectangle. This is the width of our rectangle. And this piece in the middle is also the same as the width. So if we're minimizing perimeter, that's the second equation. We need an equation for perimeter. And we've done this before, but again, it was so long ago, we probably don't maybe memorize it. And we usually just called it 2L or 2X plus 2W or something like that. But we don't have two lengths and two widths. It's actually three widths and two lengths. So you have three widths right here, and then you obviously have another length over here. So it's 3W plus 2L. And those are our two equations that we are going to utilize. And we need to figure out which one do we take the derivative of and which one do we need to use substitution with. Well, you always take the derivative of the thing you are trying to minimize or maximize. In this case, we're trying to minimize cost. And we just established that minimizing cost is going to be associated with the perimeter of this. So we want to take the derivative of this. That's what we want to take the derivative of. But we don't know, well, do we need to take the derivative of W or L? And that's where the other equation is going to come into play. We want to make a substitution. We only want to take a derivative over one variable, not multiple variables. So we're going to take this equation. You're going to choose a letter. It doesn't matter which letter. You're going to either substitute for L or W. I'll substitute for L. Or also, it doesn't matter. I'll divide both sides by L. So that means W is equal to 1.5 million. Instead of writing million, I'm going to just take out million and put times 10 to the 6 over L. Now we're going to substitute that in. We're going to substitute this into W right here. So the perimeter is equal to 3 We're going to make our substitution for W, which is 1.5 times 10 to the 6 over L plus 2L. This is now what you want to take the derivative of, and now you have everything in a single variable. Everything is now in terms of L, so you can take the derivative of L. But before I take the derivative, let's just kind of look at what we have right here before we just jump into it. You need to think about, when you take the derivative of this, what's going to happen. The derivative of this piece right here, the 2L, looks pretty straightforward. It's not going to give you any problems. But this one is. You have an L in the bottom, so how do we take the derivative of that? Well, we want to rewrite it with the proper exponent. I'm also going to multiply that 3 into the 1.5 times 10 to the 6, just to kind of clean things up. So I'll do that first. Let me multiply that 3 across. So it's 4.5 times 10 to the 6 over L plus 2L. But the best way to handle that L down there in the denominator is to rewrite it L to the negative 1. And this is going to make the derivative a lot easier. So it's 4.5 times 10 to the 6 times L to the negative 1. As soon as you see that, I'm sure a lot of you are like, oh yeah, that's, we've done that plenty of times. And now that derivative is going to be far easier to take. Plus 2L. And if you remember the basis of minimizing and maximizing, if I kind of go back in my notes, again, it was a long time ago, optimization is we are going to take the derivative. It says differentiate, this is in step 5, differentiate such that your values can find minimum or maximum values, finding critical numbers. If you recall what a critical number is, this is when you take a derivative and set it equal to 0. We want the derivative equal to 0. So we're going to take our derivative of this function of DDL of 4.5 times 10 to the 6, L to the negative 1, plus 2L. And we're going to set it equal to 0. So let's now take the derivative. So negative 1 times 4.5, so it's just negative 4.5 times 10 to the 6. L to the negative 1, we're going to reduce it by 1, so it becomes L to the negative 2. Whoops. Plus, well, the derivative of 2L, that's an easy one. There's nothing, we just use the power rule, it just becomes 2. We're going to set this equal to 0. Now all we need to do is take this equation and solve it for L. And at first this might seem a little ridiculous. You have negative 4.5 million times L to the negative 2 plus 2. But that 2 actually is pretty significant because of the way we're going to handle this L to the negative 2. Let me rewrite it like this. Negative 4.5 times 10 to the 6 L squared in the bottom, because it's a negative exponent, plus 2 equals 0. Now the best way to get rid of that L squared in the bottom is multiply both sides by L squared. Multiply everything by L squared. So I'll do it like this. Multiply everything by L squared. That way you get this L squared down here. That's completely gone. So you're left with negative 4.5 times 10 to the 6 plus 2L squared. And then the right-hand side is still just 0, because 0 times anything is just 0. This is a lot easier to solve if you do that little trick of multiplying both sides by L squared, because now you notice all you're going to do is put that 4.5 million on the other side, divide by 2, and then square root it. So we're going to add both sides. This 4.5 million So you get 2L squared equals 4.5 times 10 to the 6. Divide both sides by 2. What is that? 2.25? And then, one step away, to find the length of the rectangle, square root both sides. So the length is, might be helpful to have here. Actually, it's 2.25, so that's probably a perfect square. In the thousand, it's 1,500, I think. I'll just double check that just to make sure, but I'm pretty sure that's 1,500. It is. So, all that, quite a bit. We have now found the length, the proper length, in order to minimize the cost of this fence. It isn't all the information we want, but we do know that these lengths have to be 1,500. So we do need to ask the question, if the lengths have to be 1,500, what do the widths need to be? So now I'm going to go back to the original equation that I had written down, that 1.5 million equals length times width, because there's only two variables in there. Plug in the 1,500 for your length. So there's my 1.5 million area equals length times width. The length is 1,500 and the width is what we're going to be finding. Pretty simple to find. Divide both sides by 1,500 and we're going to have an answer. I think that's just 1,000. So the width has to be 1,000. And these are all in feet. So it says, how can he do this in order to minimize the fence? Make the fence these dimensions. That is the best way to do it. You can try other numbers, and you'll notice that if you want to keep that 1.5 million constant, you're going to require more perimeter in order to do that. This is the smallest perimeter with the greatest amount of area, keeping that 1.5 million square feet fixed. I know this goes back, we haven't seen this in a while. Is this kind of ringing a bell, though? We comfortable with this? Any questions? If anything, you just throw messages and I will make sure to answer those. So I'm going to actually go back a page and we're going to do one where we're going to answer one with an equation. The reason I skipped this one just to start off today was because I think the other one was a little bit easier. This one is maybe a little bit harder, but I don't think it's too hard. But I'll give you a second to ask any questions. If not, you can turn right to this page, and then we'll do this one. All right. There's no questions, we will jump into the next one. You'll notice I did make a slight change to it, mainly because it's obviously a typo. It says find the point on the parabola. It says y equals 2x. Y equals 2x is not a parabola, so it is y squared equals 2x. And you'll notice that it's y squared, not x squared, which is still a parabola, but it is a sideways parabola. So if you were going to throw this in a graphing calculator per se, you would need to graph y equals plus or minus the square root of 2x. You need to graph two separate functions, y equals square root of 2x and negative square root of 2x, in order to get this sideways parabola. Normally, I would probably throw in a graphing calculator. We'd graph it quite accurately and so forth. I'm not going to do that. I'm just going to sketch it as best as I can. But that's the parabola, especially for a parabola that is y equals, or y squared equals something. The parabola looks like that. And the question says, find a point on the parabola that is closest to the point 1, 4. So let me put 1, 4 somewhere. 1, 2, 3, 4. You probably can't see my dotted lines very well on the screen. I can't even see them on the screen. But 1, 4 is right there. And they're asking, what is the shortest distance? It says, or that's basically how we're thinking of it. What is the shortest distance? Obviously this line and this one. Obviously the second one I drew is shorter than the first one. So they want to know what point on the parabola. So it's going to be somewhere in here. Which one is the closest? That's what we want to know. We've got to figure out exactly where it's closest. And there's a few things we could do here to kind of figure that out. It's going to be closest where it is going to be perpendicular. So it does look like it's going to be somewhere over here. But again, just be aware that I didn't graph this parabola accurately, so I can't use, I can't just use the graph as a method of finding the point. We're going to use optimization and figure out exactly where that point should be. So the first thing is we need to come up with two equations. And luckily we have kind of one of them already. Y squared equals 2x. That's the parabola. But then the thing that we're trying to minimize or maximize is closest, or closeness. And we need to figure out an equation that quantifies this. How do we we need an equation that shows closeness. And the best equation to use, especially on the coordinate plane, is your distance formula, which I don't think we've used in a long time, but I know all of you are familiar with it because we used it a ton in geometry a few years ago. And that formula looks like this. D equals the square root of x2 minus x1 squared which right off the bat does not seem ideal because we have to take the derivative of this. So we are going to do a little trick before we kind of jump into it. And that little trick is what we're trying to minimize is distance. We're trying to make that as small as possible. But what we're going to do is we're going to square both sides. So we're going to call this equation d squared equals, if we square both sides, that square root's going to drop. So we get x2 minus x1 squared. And the reason I'm doing this is because it cleans up a lot of the math. You don't have to do this, but this makes it a lot easier. Because if d is as small as possible, d squared is also going to be as small as possible. This, again, is just going to make it far easier. Now we need to make our substitutions and so forth in order to figure out where to go from here. Now, luckily, we actually know two of these values. We know 4 and 1 because the point is 1, 4. So one of these x values is 1 and one of the y values is 4. So let's substitute those in. So we have d squared equals x2 minus 1 squared plus y2 minus 4 squared. So we actually got rid of 2 of the 4 variables in the equation, but we still have a problem. We still have 2 variables. We have x2 and y2. We want 1 variable, so we need to make a substitution using this right here. So you can either choose to solve for x or solve for y. And when making that decision, it's best to think about what is easier to do. So if I solve this equation for x by dividing both sides by 2, you get y squared over 2 equals x. Or you could have square rooted both sides. Either substitution, I'm going to let you know, is going to work. One of them is easier than the other. And we know when it comes to taking derivatives, taking a square root derivative is not always the easiest thing to do. So use y squared over 2. So we're going to make the substitution in for x. This is another way to simplify the problem. Now again, these are just little tricks to simplify it for myself, but you're going to get the right answer regardless, as long as you do everything correct. But obviously, if you make it more difficult for yourself, there's a higher chance you might run into a mistake. And I'll let you know right now, I actually tried this both ways earlier. The square root of 2x actually was very hard. It took a long time, but it did work. So we're going to use the y squared over 2 substitution. So anytime we see an x, we're going to substitute it with y squared over 2. So we have d squared equals, there's the x. We're going to substitute that with y squared over 2. Minus 1 plus, not substituting anything in for this y. I'm not going to use the subscript anymore. It's not needed. Minus 4. Now you have a function. Everything's in terms of y. Everything else is substituted in. We are ready to do our optimization, meaning take the derivative, set it equal to 0. So we're setting the d squared equal to 0. And we're going to start taking this derivative. And you might recall that these derivatives, maybe not the nicest thing, but you have a chain rule here. You could expand it if you prefer. You can go through your FOIL or your box method or whatever. Make it easier for yourself if you find that easier, or you could just jump into the chain rule. So if you remember our chain rule, outside first 2 times the whole thing. So you're going to rewrite what's in parentheses. Y squared over 2 minus 1. Then reduce that exponent by 1, so it becomes 1 times the derivative of the inside. So what's the derivative of this? Well, the negative 1 just goes away, and then you get 2y over 2. 2y over 2, which the 2's can cancel out. Now let's do the derivative of the second part. Same thing. We're going to take the chain. We're going to chain rule to this as well. So it's plus 2. Rewrite the inside, y minus 4. Reduce the exponent by 1. And the derivative of the inside is actually a little easier than the other one, because the derivative of this inside, the negative 4 goes away, and the y just becomes a 1. And that's our derivative. Let's clean this up. This is obviously not the most the best looking function we have here. I'm going to get this y over here. I'm not going to distribute just yet, just to make it a little bit easier. So I just moved the y from the right hand side of the parentheses over there just to clean it up. Plus, and really the only thing I can do to clean this up is I could distribute this 2. Because this 1 doesn't matter. So you get 2y minus 8. All equal to 0. So our goal is let's just solve for 0. Or just solve for y rather. Let's distribute the 2y across here. This actually works out quite nicely. This 2 cancels out with this 2. So you just have y squared times y, which is y cubed. Then you have 2y times negative 1. Well, that's easy. It's just minus 2y. And then we're going to rewrite everything else. Plus 2y minus 8 equals 0. Well, that's nice. You have a minus 2y and a plus 2y. They just combine like terms. They're gone. So you get y cubed minus 8 equals 0, which is, we are really leading into something great because this is going to be super easy to solve. Add 8 to both sides. Cube root both sides because 8 is a perfect cube. You get y is equal to 2. Now we need to figure out the x coordinate. So we're going to go back to the original equation, which is that y squared equals 2x. So y squared equals 2x. We now know what the y coordinate is. Then this is a little bit strange. We're plugging in a y coordinate to figure out an x coordinate. Usually it's the other way around. But it's fine. We know what the y coordinate is supposed to be. We know it's supposed to be 2. So we're going to plug in 2 for the y and figure out what x is supposed to be. So 2 squared is 4, which is equal to 2x. We'll divide both sides by 2. And we get x is equal to 2. So you get y is equal to 2. You get x is equal to 2, which means the coordinates are 2, 2. So let's kind of remember what we just found. 2, 2 is the spot on the parabola where it is closest to 1, 4. So 2, 2 is actually right here, not on my parabola. It would be somewhere probably over here. If we graphed it perfectly, obviously that point would exist, but it's saying that this distance from here to here is the shortest possible distance that exists between that point and a spot on the parabola. Any other line we were to draw would be longer. And another way to think about it is it should be perpendicular to the curve, at least at that spot. It's a weird thing to say perpendicular to a curved line because, lines are curved. It's hard to be perpendicular to something that's curved. But if we think about it on a very small scale, it should be the spot that would be perpendicular at that point. Every other line will be longer than that point. So it's a little interesting thing that we could have found. And you can kind of test this out using the distance formula if you wanted to do it a bunch of times to prove to yourself that that is in fact the smallest distance. Go ahead, be my guest. You can do that on your own. But we're not going to check that. That's a lot easier to check when we're doing, when we're talking about perimeters and areas. Probably not distance formulas. So I know this is just kind of a big recap into optimization. I just wanted to kind of get us in the swing of things with the feel of kind of the format that we're going to be doing from here on until we return to school or possibly the rest of the year. We will see. Because the very next thing we are going to get into, I believe, is the antiderivative. I think that's the next part of our notes. For some reason, I don't have them in this packet. I'll have to pull them up. We're not going to start them today anyway. Because it's going to take more than, I only have about 7 minutes left. So I think I'll just end it there just to get the swing of things. Please send me reminds if you think you will work. I can get you that work. I can either email them to you, and that way you can submit them to me if you're concerned about your third marking period, well, now fourth marking period. I will start posting assignments on Google Classroom. Again, not that frequently. Every now and then. We'll have one. That way we have that way I have something to give you a formal and proper grade on. All right. I'm going to stick around here for a few minutes. If you guys have any questions that you want to type to me or if you want to send it to me on Remind, just let me know. But I'll keep everything going. I thank you guys for showing up, especially on our first day of doing calculus like this. We're not going to do this every day. I'm doing every day with my Regents classes, but not with you guys. I'll do the next day we meet will be on Thursday. So we will meet on Thursday, same time, 1 o'clock. But we are all done for today. Thanks for showing up. I'll see you guys later.